parts of the test itself. So section 9.5 is where you see a complete test. Let me say this right now before I forget. I'll see if I can remember to say it again. Section 9.5 homework tells you to go use a worksheet in the back of the book, right? Screw that worksheet. You're not going to use that worksheet. That worksheet is for crazy-ass professors who have their students pushing buttons, getting answers. We're going to use the 5 steps that I gave you, right? So you can use that sheet, that one sheet about the coyotes. It's got all the explanation for all the steps. Okay. I like it. If there's no questions, I want to kind of start off with sort of stepping back a little bit and then filling in a couple of things that we haven't really discussed yet. And then you're not going to believe this, doing more examples of hypothesis testing. We still have to do hypothesis tests for a percentage. We haven't done any of that yet, so we need to do that still. So one thing, I think the first thing I want to do is really highlight the meaning of the various things. So two of the newest things are the p-value for sure. Right? We've never even heard of this p-value before we got to this chapter, correct? This weird funkadelic p-value. Can any of you give me any idea of what the p-value is? Does anyone remember? Like, how do you find it, or what is it visually? Yes?
It's the area with Z or T star. T,
all right.
Z scores and T scores.
So it's the area that your Z star, the area of the tail that your Z star makes, right? Okay. So, and also, let me say this. This sounds unconnected, but I'm going to connect it in a minute. You guys remember why we said way earlier this semester that 2 standard deviations away was where unusual started? Does anyone remember why that was decided? And you all agreed with me because you thought you had to, but everybody agreed with me because it made sense. But does anyone remember why it was 2? Why was it 2 standard deviations away? Anything further than 2 we considered unusual, and now we've sort of refined that based on what alpha is. But why was it 2? Yes. So if 95% of the data is within 2 steps of a normal curve, what percentage is outside of there? 5%. So what is the probability that any specific data point falls further than 2 standard deviations away? 5%. So, everybody with me? Right? So before this chapter, we just generally accepted that 5% was the threshold that we said anything that has less probability than that to happen is unusual, right? What are the chances that you see a 3'7" tall, a 3'7" tall person? What do you think the chances are? Do you do that often? Do you often see that in real life? Don't tell me about a movie you saw, right? Do you see that a lot? Can you give me a subjective probability, meaning like a guess of a probability that you would see somebody 3'7" tall? Is it 50% chance?
Less than 5.
Definitely less than 5, right? I mean, you intuitively would say that is unusual. And if you actually drew out the curve for heights, below 3'7" would definitely have less than 5%, way less than 5%. Okay. Are you guys kind of, now what does that mean? Well, how does that connect to this? Well, in a hypothesis test, the whole idea is I have a claim, and let's say the claim is the mean is something. Let's say the mean is 10, whatever. It could be greater, equal to, less than equal, so it got some kind of an equal to. So it thinks it's around that. It thinks this is in the middle. Then we say, all right, to show evidence that it isn't that, because what would the alternate be in this case?
Doesn't equal 10?
Yeah. So somebody's got to tell us, what's the level of probability that our sample, that would tell me something happening is unusual, right? So here's, I really want this to make sense. We assume that the mean is 10. If we get a sample out there, for example, right? Let's say that alpha is 0.05. That alpha is telling me anything that happens that's below a 5% chance is unusual. Okay, how does that connect to a hypothesis test? Assuming the mean is 10, if we get a sample, that it would be unusual to get that sample if the mean really is 10, it's more likely the mean is not 10. I really want that to make sense. So, I mean, if the mean really is 10, shouldn't we get a sample in here somewhere? I mean, a large percentage of the time, we're going to get a sample in there, right? So if we think the mean is not 10, and our sample, sure enough, is way the shit up there, that has exceeded the threshold. That maybe this p-value, so let me give us some numbers here. Can anybody tell me, let me see if you guys remember. Let's say this is a z-score situation, right? I'm not going to get into too many details. What would the z-score be for this situation? 0.05, two-tailed test. I don't think you necessarily have it memorized. Yes, 1.96. And let's say we get 2.13, let's say. Let me stop for a minute. The z-score very directly tells me this is the benchmark for how far away my sample has to get. So obviously we have gotten far enough away, right? We are much further away than 1.96. Is that cool? The p-value gives us another way to look at this. It says, okay, what's the probability that we would get a sample in this area? And that's when we look up to 2.13, we get the area from the chart. So alpha tells me, normally it's 5%, it could be 1%, and then I've got to find a sample that is more than 1% unlikely. That is, it's that unusual, right? So the level of difficulty of passing that test increases when they make alpha smaller, because now it's got to be further out. So, on one level, I can just compare z-scores and be done with it. But remind me, where did this z-score come from? That came from the alpha, right? And what did I tell you? In the real world, there ain't no alphas. There's no alphas, right? And this is not a class about alpha males, beta males, but there's no alpha levels. So, try this. So it's still this idea of somebody thinks the mean should be around this. How do I show that looks to be wrong? I find a sample that is so far away from there. And what sets up what's far enough away is alpha. So alpha is if I get a sample that has a smaller chance of happening, then that means that's evidence that the mean is not that. The mean is actually different. So if the p-value is less than alpha, we can reject the null. Because, I really want this to make sense. The null thinks it's in here somewhere. Is everybody cool with that, what I'm saying? The null thinks it's in there somewhere. It thinks it could be equal to that, yes? The null has equality, so it thinks it's in there somewhere. So if I get a sample that would be unusual, if that was the real mean, then more than likely that isn't. That's why I can reject the null if I get a sample so far away. Okay, maybe. Okay. Let me see. Do they want to do something else in general? Yes, that's right. All right, one more thing. erase this. I'm going to do this next thing in two different ways. Tell me, what are the two possible outcomes? There's really only two possible outcomes to any hypothesis test. What are they? I mean, if we get into the rejection region, what does that mean? I can do what? Why do we call it the rejection region?
Because you agree with the other side?
Not really, you don't agree, you just find evidence. What do you mean the other side related to what?
Against, I don't know, I'm like getting my words mixed up
I
right
understand.
now, I'm trying to find the word.
All right. So if we do find something out far away, then the one who thought it should be in here is wrong. We found evidence that they're wrong. Right? So if we do find something really far away, I can reject the one that includes it might equal that number. So again, just like we had a second ago, if the null hypothesis is that the mean is 10, so somebody believes that the average number of hot dogs that some group can eat is 10. Right? All right, they're going to do some hot dog eating competition. You with me? So they think the average number of hot dogs that these people can eat is 10. How would I prove they're wrong? I would give them a bunch of hot dogs, and they would eat either a lot more than 10, yes? What if they all ate 20 hot dogs on average? What would you think about this dude's claim? That it was going to be 10. I predict you're going to eat about 10 on average. And they end up eating 20 on average. Just on the surface of that, what do you think about his claim?
Wrong.
Was he right? He was completely wrong. Because what if they would have eaten and gotten 11? What if they would have gotten an average of 11? Wouldn't you go, oh, you got close enough? Do you guys get that feeling? Yes, maybe? All right, maybe. I'm really sorry if you hate hot dogs. Just got to pick some kind of example. So, if they do get like 11, that is close. That's close. I mean, that's pretty good. I'm like, wow, that's pretty good, dude. Right? But if they eat like 20, now that more than likely that's pretty far away. We'd have to know the standard deviation, but that's pretty far away. We'd say that your guess was wrong, dude. You're way off. I'm going to reject what you said. So the null always has some kind of an equal sign in it, right? It's going to do this, this, or this. So it always has the possibility that it's in here somewhere. So how do I show that person is wrong? I get a sample that is somewhere else. That's further away from the mean than that little acceptable area. Maybe. And that relates directly to the p-value, because the further away my z-star gets, the less area there is out there. So the smaller the p-value, the more significant our findings. That's why another name for the alpha is level of significance. I think I've used that phrase on one of the handouts at least. I can't remember. Okay. So the two things, I kind of went back into the other. The two possible outcomes are I either reject the null. Yeah. Right. Which also means support the hot. Those are both the same thing. So that's not two separate things. If I reject the one dude, I support the other dude. Right? What's the other thing that could possibly happen? So this would mean we got far enough away. What's the other thing that could happen? If one situation is we got far enough away, the other situation is, if one situation is that we got far enough away, the other situation is we didn't get far enough away. So if we can reject what the null says when we get far enough away, are we able to do that if we don't get far enough away? No. So the other thing that could happen is fail to reject the null. So if you reject the null, it's the same thing as saying support the ha. Basically the same thing. If you fail to reject the null, then you fail to support the ha. The alternate.
Why is it that you never agree with the null?
Because, and let me know if you have a problem with this, but I've said this a few times. Let me know if you really have a problem with this. You can never prove that the population mean or percentage equals something with just the sample. So I'm never going to be able to agree with the one that it might equal. Because I can't do that with a sample. But if somebody's like, I think it's 5, and we get a sample and it's 487, that is evidence that it isn't 5, right? Okay, so we can show evidence that, through a sample, I can show evidence that it's different. But I cannot show evidence that it's equal to. Okay? Because if somebody thought it was 10 and our sample came out to be 10, does that mean that it's actually 10? No, it just means that we fail to reject it's 10. Maybe it isn't 10, but our sample didn't show that. Same thing as you get found not guilty. You never get found innocent. You can only show evidence that somebody did something. You can't show evidence that they didn't do it. Okay, maybe. Okay. So what this leads to, this is going to be a little weird because even if we do the whole problem correctly, is there a chance that what we say at the end is wrong? So if we reject the null, is there a chance that we're wrong? What do you think? Hell yeah, man. That's what statistics is all about. Statistics is like, I think it's this. All right. Okay. So there are 2 types of error that can be made. 2 types of error when you do this kind of problem. Even if you do it perfectly, every statistics problem has a little bit of allowance, right? When we make a confidence interval, we can never be 100% confident, correct? There's always some percent chance that we're wrong. So one type, we got really creative with these. We have a type 1 error. And the type 1 error is, what if we reject the null, but it's actually true? So, in this situation here, let's say the null is, the mean is 10. So the alternate is, it's not 10. Is it impossible, so we set up our rejection region, right, blah, 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 blah. Is it impossible to get a sample here, but the mean really is 10? Is that impossible? What's the probability? So remember, this was alpha as 0.5. What's the probability that I get a sample in the rejection region, that I get a sample out there? What's that probability?
5%.
5%. Holy shit, yes, right. Alpha is the area in the tails. Area is probability. So there's a 5% chance that I can get a sample that far away and that the mean really is 10. I just happen to pick a crazy big sample, a crazy small sample. So if I go out and take a sample of people, could I just randomly get a group of older people? I didn't try to pick older people. I just randomly get older people. So then my age, sample mean age is going to be too high. Okay. So the actual probability of rejecting the null when it's actually true, that would be a mistake, correct? If we thought the null was wrong and in reality it's right, that's an error. So the type 1 error is rejecting a true null. So what do you think the type 2 error is? what's the only other thing we can do? We can either reject the null, and when is that wrong? It's wrong to reject it when it's actually right. So what is the other thing we can do, and when would it be wrong?
Fail to reject.
Yes?
Fail to reject the true.
No.
null. Wait, no.
When do you want to reject it? You want to reject it when it's false.
Yes.
So when would you do something wrong if you fail to reject a false? So if the null statement is actually false, but our sample just doesn't get far enough away, there's an error that's been made. The crazy thing about statistics is you're never gonna know. Because we're studying shit that we don't know anything about, right? We go to an island, we find a new species, and we're curious, what's the average weight of this thing we just found? So we take a sample, and we think it's this, and we say, I think it's actually heavier. So we take another sample, and we do it, and we do a test. I don't know what the reality is. I don't know. But I want you to realize, why does this change? What is that the probability of again? Can somebody remember? What is alpha the probability of? It's one of these two things. You got a 50-50 shot. When do I reject the null? When I get a sample out here. What's the probability that a sample would fall out here?
5%.
5%. If that's really the real mean, a sample has a 5% chance of falling out there. So alpha is the probability of this. So if the type 1 error for whatever you're doing, this is sort of like when I kept talking about if you had a nuclear power plant, when would you get off your ass? So if making a type 1 error leads to catastrophic outcomes, then what do you want to do with alpha? If you don't want to make a type 1 error, what do you do with alpha? Making a type 1 error is horrible. What do you do with alpha? Make it smaller, right? If you don't want a type 1 error to happen, what do you do to the probability of a type 1 error? You make it smaller. Now, we're not used to being able to control probabilities, right? That would be neat if we could, right? You're like, let me change the probability that light turns green. That'd be awesome. Can't do that shit. But with these tests, that's why they sometimes change this. One reason is because a type 1 error would be either really catastrophic or not that big of a deal, right? Then you can change the probability. What do you think happens to this type error if I decrease the type error 1 happening? Obviously, what should happen to this one? If I decrease the chances of a type 1 error.
The chances of the second error goes up.
Yeah, of course. You can never get something for nothing. So if you want to decrease the probability that 1 error happens, the other probability goes up. Maybe. So let's do a non-mathematical problem that deals with this. One of my go-to examples is if you're a medic on a battlefield, right? You're a medic out in a battlefield, so you're a battlefield medic there. So you're the medic out there, you go out, something just happened, the enemy's now going out that way, you run out to the field, there's all these bodies. What are you gonna go look for? What are you gonna try to do? You come up to a body.
Check their pulse.
Why?
Because if they're dead, there's no point.
Yes, good. Right? If they're dead, I can't do anything, I move to the next person. If they're alive, I'll try to help them. Yes? That's battlefield triage. So, in this case, what is it? Let me really make sure that you get this in the right place. When you come up to a body, what are you looking for evidence of? Life, right? So the alternate hypothesis is the person is alive. I'm trying to find evidence that they're alive. So what's the null hypothesis? They're not alive. 11. Person is not alive. Maybe they're zombies. Whatever they are, they're just not alive. Can somebody tell me what the type 1 error would be? So the way I remember the errors, let me kind of give this away a little bit. Type 1 is the shorter phrase. Reject a true no. That's type 1. Reject a true no. If I reject something that's true, that's an error. Type 2 is the longer phrase. Fail to reject a false no. Holy shit, that's type 2. So what's a type 1 error? What's true in a type 1 error? Or is the null true or false in a type 1 error?
The null is true?
Null is true. So what does that mean physically here? Person's not alive, right? So the person is not alive. That's true. The null hypothesis is true, but what do we think? But we think what? We think they are alive. Why would that be bad? You're all like, great, man, this is what I want to talk about on Thursday. People dying in the field. But, oh, why is that bad?
Because it could be another person that's actually alive.
Yeah, you're wasting time on somebody that you can't really resuscitate in the middle of a field. They're already passed away. You don't have the equipment to bring them back. You're wasting time, right? But let's look at the other error before we figure out which one's worse. So what's the type 2 error? So type 1 error, the null is true, but we think it's false. We reject it. Type 2 error, the null is
Wrong.
false. In reality, it's false, but we think it's true. So type 2 error, what's actually happening? Say again? Yeah, the person is actually alive, because this is false. The person is alive, but we think they're dead. Now, the question about which one's worse, I don't know, that's a hard question. Because one, you're wasting time, and the second one, the person on the ground is experiencing a horror movie. You came to them and like, oh good, and then you left and you're like, okay, this is too bad. Right, you guys kind of with me? I know, it's a morbid example I picked, but I like this example because it's very visceral, and this is related to decision making, right? This is what this really is all about. How do I make decisions? Not every decision we make is going to be freaking, battlefield people die and shit, but I like this also because it's not mathematical at all, correct? This is just English, and this is just feelings. So that's really kind of, in reality, how you set alpha. It just depends on which one is the worst error to make. And I don't know. Does anyone have a feeling about which one's the worst error to make? That's a hard call, man. Because again, you're wasting time here. And here, you gave somebody hope and then walked away. That's some Game of Thrones shit right there. All right. Maybe pre-season 7. Okay. So let's do this. Let's do, I think, does everybody have the handout? I think we did one side last time. The Ford Focus side. And the other side's got credit card debt. Yes? You guys have that? So we're going to do 2 more things today. We're going to do this example. I'm going to introduce how percentages work. We're going to do an example of percentages, and then we'll look at what time it is. Of course, Sebastian is like, you should be paying me, dude. Thanks, man. Yes. yesterday, or not yesterday, you know what I mean, we did the Ford Focus one. Yeah. This one, so what I want you to do, I want you to get as far as you can. Then I'll come in, we'll do it together, and then I'll discuss what the types of error would be, or specifically what type of error we could have made. So it's gonna depend on what our results are. So try and get as far as you can with this. If you don't have this, let me know. Make sure everybody's on the right track, and then it kind of starts to catch up to you a little bit. just gotta figure it out, Z or T or nothing. T, that's right. So what's the first thing I should look at? What tells me I can do something? Yeah, why is this one normal? Yeah. Like, so n is 81 greater than 30. Central limit theorem says normal enough. And then I can tell the difference between the two. What do I look at? Yeah, it's the standard deviation from a sample, and obviously, not obviously, you gotta be a little careful. From a sample, we found this stuff. So the standard deviation we have came from a sample. So sigma unknown, only know S.
It's unknown because it came from a sample?
We don't know the population standard deviation. The only standard deviation we have came from a sample.
Okay.
So we don't know the population standard deviation. So yeah, T-scores. Question. Alright, so what's my degrees of freedom? 8. And my alpha is 0.01, and it's a one-tailed test. So now I know exactly where to look at. 0.01, one tail. So that's the second column, right? And then I just stop at 80. 2, 3, 7, 4. Now when I say define the rejection region, what that really means is draw it. That's why I say put it into words also. So I want it drawn, and I want you to put it into words. What side is my tail on? Yeah, so it's up here, because it's greater than, so this, the great thing with inequality symbols is they're very often seen as arrows. Same thing here, it's an arrow pointing you where the tail is. And then we just figured out something that I've forgotten, was it 2, 3, 7, 4? Yeah, okay. So it's not negative because it's up there. It's not below the mean, it's above the mean. So how do I put this into words? How does a sample get in here? If it's
T-star.
good, if the T star,
Greater than 2.374.
yeah. Then I can do what?
We can reject the whole.
Reject the low,
Support hop.
support the hot. I like it. Again, that whole idea is the null thinks it could be equal to this. So the null thinks it's in here somewhere. So if I find a sample way up here that is evidence, and in this case, really good evidence, because that's only got a 1% chance of happening. So if I do that, I found really good evidence that the guy who thinks it could equal this is wrong. The other guy looks to be right. Okay, that's the whole idea of a hypothesis test. Now I say this, I mean, if you don't write it all down, you're fine, but I just say it just to kind of be nice, but what's my X bar? Nope, it's N.
12.
Yeah, 12, 57, 34. What's my S? Yeah, 3. what did I wrote over mine? 306.25. And can I make a T-star score now? No, good. Why? Special dude. I like it. People don't understand this because some people think when you do sigma X bar, you're making a sample. No, you're not. You're taking it from an individual spread to a spread of groups. S is an individual spread. I still got to take it to a spread of groups of 81. 34.03 in stops. 028? Okay. Okay, so you're a weird freaking stats instructor who wants you to take it at least 3 places. Now see if you can get that T-star score, if you haven't already. How do I build this formula? What goes first here? Yeah, my data, so the 1257. And then it's always minus the number from the claim. That's what we're going to assume the middle really is. So we're assuming the actual mu is that, 1193.12, divided by the new spread we got. Sounds about right. 1.89. All right. So we're going to concur. Okay. And right there. Now again, I want to remind you guys. I don't know if this makes sense to everybody, but your T-score chart. If I wanted to be able to ask you what the p-value was for this, I would have to give you a z-score chart's worth of information for every degree of freedom on your t-score chart. Every degree of freedom I would have to turn into its own sheet and give it to you. So you'd have a little volume of, you don't want that, do you? Please tell me you don't. I'm not going to print all that shit out. So I'm never going to ask you for the p-value. You can't look that up on the z-score chart because it's not a z-score, is it? It's a t-score. Okay. There is a way you can get something from the t-score chart. Do I want to tell you? Maybe. What was the degrees of freedom again? It was 80, right? So watch this. If you look at 80, and our t-score was 1.89. Can you see where, isn't 1.89 in between these two? You guys see that? So it's in between these two, so my p-value would be in between. It was a one-tailed test, right? So it would be in between these two. So that's as good as I can do on the t-score chart because it doesn't give us enough information. Because it has to do so many different degrees of freedom. I don't know if that makes sense, but at least take away the fact that I'll never ask you for a p-value for t-score. Maybe an extra credit. But even without the p-value, you can still answer this. Did we succeed? Did we find evidence?
No.
Exactly. We did not find evidence. We didn't make it this far. We only made it this far, roughly. I don't know, somewhere there. So we failed to reject the null. Failed to support. Huh. I like it. So how do you pick which one is gonna govern how you answer the conclusion?
Fell to reject. Oh.
Yeah, because what was it's not gonna be that one. What was our claim? What was our claim? Which one, HO or HA?
Oh, HA.
HA, so I want to use the one that talks about the claim. Really want this, both of those say the same damn thing. It's like me saying, I'm older than Bob. And then I say, Bob is younger than me. Didn't I just say the same damn thing twice? Those two statements say the same thing. If I fail to show that the null dude is wrong, I fail to show the other dude is right. They just go right together with each other. But the way I word my conclusion has got to be related to the conclusion. I mean, to the claim. So we failed. So what does that translate into? Did we find evidence? No, we have not found sufficient evidence. Two, support the claim that what?
The average credit card debt for all students in college has increased.
Average credit card debt for all college students has increased. Woo. I don't know. Those of you with credit card debt might feel different. I know my university years are very plastic life because I was only allowed to work so much, so it kind of was amazing. Anyway, all right. So, might as well stay up here. Let me just find some paper. Well, this will work. All right. So now we got to talk about what's going to change when we do a hypothesis test for a percentage. The really good thing is very few things change. Still the same 5 steps, still the same interpretation, all this kind of stuff. But obviously, 2 of the things, well, let's say 3. One of the smallest changes is I'm not going to use this symbol if I'm talking about percentages. So that's a given. You better put a P here if you're talking about percentages, right? Another thing that's going to change is right here. Am I going to be able to say n greater than 30 if I have percentages? What do I have to check if I have percentages to see if it's normal enough? Yeah, NP hat, NQ hat, and in this case we're actually going to do NP and NQ because with hypothesis tests we assume the claim number is true. So we need NP and NQ to be at least 5, right? So the step C is going to change, step B is going to change a little bit. And this is the one that's going to change a decent amount. So we need to talk about this. So let me see if I've got some paper. Maybe I can stay up there. Bum, bum, bum. Oh, there we go. All right. So we got any questions from that? Okay. So what's going to change? So right now, for example, Z star is this. And T star is basically the same thing except, T star would be this. So basically T uses S where Z uses sigma, correct? Just like in our confidence interval formulas. Those are the formulas we've been using. They're basically the same formula, right? When I have NP and Q, I don't have any of this shit. And what I want you to remember, who remembers, what's the confidence interval formula? Actually, anybody give me any confidence interval formula? Anybody?
X bar plus minus Z times
which piece of this is the standard deviation we're using for this problem?
Sigma over.
Yes, sigma over square root of n. I love it. That's the spread number, correct? Now, what's the one for p hat? Sorry, anybody remember? C there.
And then p hat times q hat over the,
I got you. Now watch. They're both basically the same. X bar and p hat are our sample information. That's our best guess. Give or take, a z-score, or in the case of x bar, could be t, something that tells me how far to go. And the next thing is the spread. So therefore, what is this? That's the spread for a percentage problem. That's the spread for an NPQ problem, like a hypothesis test. That's the spread. That's the standard deviation. So watch this. This is coming. When I go to make Z star for a means problem, I do my data minus the supposed middle divided by the spread, right? So when we go to do it for p hat, it's going to be our data, it's the p hat one, right? Because that's the one that comes from the sample, minus the p from the claim. So the claim is going to be something like, I think that the percentage is at least 50% or something, right? So that'll be p 0.5. We're going to assume that's correct. So p hat minus p over the spread. And the one little thing that changes here, in this case, I had no idea what p and q were. In fact, that's the whole point of making a confidence interval, is to improve on our p hat guess for what the real percentage is, right? That's the whole point of a confidence. I don't have a freaking clue what p and q are. In a hypothesis test, we assume that the number we're working with in the claim is the real thing. So we're not going to use the hatted ones down here because we're assuming that this is the right one. So on that fourth step, we're still going to calculate a Z star. We're just going to use the formula that's got percentages in it. Yes?
Bottom's only square root of n.
How do you mean?
For the bottom, did you get rid of the p and q? Or
No, they're right there. What's happening?
you crossed it out?
No, this is a divided line.
Oh, my
Yeah,
bad.
that's right, that's right. Yeah, the whole point there was they're just not the hatted ones because we're assuming we know what P is. Okay, so. It's gonna blow your minds, but I have, of course. Just wanna see how many of these I can do before people start staring at me. Alright, so let's take a look at this guy here. Oh, it's really nice here, I put it down there. Alright. It's always interesting to me, I don't know, students are always like, I want more examples, and then I get to this part and they're like, that's enough for the examples, but we haven't done one like this really yet, but it looks the same, right? So what is the claim that's being made here? Who's making a claim?
Chicago policemen.
All right, what's their claim?
That those 55% Chicago residents have an unfavorable view of their local.
Cool.
police.
Now take that English and transform it into Mathish. What do they think about the percentage of Chicago residents who have an unfavorable view of their local police? What do they think that percentage, what do they think is true about that percentage? I'm gonna put a P down. They're making a claim about a percentage. They think that percentage is at most 55%. So how do I translate that into Mathish? What does that most mean?
Would that mean P is less than or equal to?
Good. So at most is this. It's a ceiling. You could be at most this. You could be at most 12 to eat off the kids' menu at Denny's. So the 13-year-old's like, ah, shit, right? Okay, I don't know if that's true, to be honest, but it sounds right. So at most means less than or equal to. And of course, please, dear God, percentages, write them as what they are. They are decimals. We just made them look like a percentage because we're humans and we like that. Math needs them as decimals, right? Cool. Now, everything's the same. This is awesome. There's only a few things that change, right? Where does that go? Let's make this a ha. I gotta update all my little worksheets, but does it go for the ho or the ha? Which one? Oh. And so what is the ha gonna be?
The.
Greater than?
Yeah.
Greater than. I love it. So of course you write the claim down, and then you just take a second. Does it have an equal sign in it? Then it goes into the null, HO. If it doesn't, it goes into the null. And whatever you wrote, the opposite thing goes into the other one. What do you look at to see how many tail tests this is?
If O is completely equal.
No. Well, let me say this. Not just how many, but where it's going to be even. Right? One or two tail and where the tail will be. What do you look at? The ha. So I really want, never forget this. Any statement that has an equality in it, I cannot show evidence for that through a sample. So the way we've set this up, it is always the alternate one that we can find evidence for. So that's what sets up where our evidence starts. So where's the tail going to be? It's going to be one tail. Oh, hello. Yeah, so one tail. Now on this problem, I'm really nice. I think normally I'm kind of nice. Do you see how I didn't even mention t-scores? I'm trying to help you out a little bit. Remember, they were invented for means. This is going to be a Z or nothing. So what do I check to see if we can use z-scores?
If the number is above 30?
Nope. That's for means.
Oh.
Greater than 5.
Yeah, in this case, again, we're assuming that P is this. So I'm going to check NP, and I'm going to check NQ. For confidence intervals, we had to use P hat and Q hat because it's all we knew. We had no freaking clue what P and Q were. Here, we're going to say, okay, let's pretend like it's 0.55. Let's see what happens. So we know that P is 0.55. What's N? Who?
Oh, N or Q?
N.
996.
Good. All right, so 996 times P, and of course, I think you just told me Q. You guys good? Five 547.8. And then this one's going to be 448.2. And those are both at least how much? 5. Check, normal enough. So if either one of those fails the check, if either one of those is less than 5, you officially can't do anything. Okay. So now I've got the rejection region. I know it's up here. I know alpha is this. I know it's a 1 tail. I know I'm using z-scores. So of course I'm going to look at my z-score chart, right? Which column are you looking at? First one. I like your .05, 1 tail. And then I just go, where do I stop? No, I stop at the end. I want a z-score. If I stop too early, I get a t-score. We know we want a z-score. So you only have to worry about degrees of freedom if it's a t-score you want. So that's our good old 2576. We've seen that before. So what would this look like in words if we get a z star that is, how do I get in here? Greater than 2576, then we can do what? Reject. The null, I like it. And support. Say that one dude looks to be wrong, you can say the other dude looks to be right. So go ahead and do part D. Finish part D. Get what Z star is. Take this to at least 3 places. Understandably, easy place to make a mistake. see, I don't need to calculate Q hat, do I? I don't need Q hat anyway. So what am I gonna put inside the square root symbol? Goes here. Yeah, P is 0.55. Q is 0.45. Divided by N. So now it's all about getting that whole thing into your calculator correctly. They have that. How much?
2.92.
2.92, yeah. You might have, I don't know, did you round this one? I mean, did you take this out further? Why just shoot 596?
I rounded it to 4.
Oh, 4, okay. You're fine. They're good. So that one, it just has to be at least 3, so you can make it 4 to kind of match all the other probabilities we've ever done. That's fine. What about the p-value? So where's that 2.92? It's so we got right here, 2.92. So what is the p-value? It is the what?
The area above that.
It's the area in the tail that your Z star makes. So all you gotta do, this is an old problem now. I just wanna know what area is in the tail of 2.92. I wanna know what this area is. Yeah, this is, wait a minute, 0008, sure.
I got
They make it down, so let me see.
details on there.
292.
I looked at 294, that's why.
Oh, you're good, you're good. You're fine, you're fine. So yeah, I always leave it open that somebody can take this out further, so you're gonna be a little different. I get 9982 here, but of course, that's not the answer. I want this one. This is old stuff, right? Now, of course, you know, I say old, when it's actually like a few weeks ago. So I just gotta find this area up here, so that's gonna be 0.0018. So the p-value is 0.0018. That is pretty small, yes? That's like a 0.18% chance that we would get a sample where we did if 0.55 was the real middle of the picture. So what's more likely? We just happen to do something insanely unlikely, or the real middle is higher?
Question.
Yes.
So, my original thought process, minus the fact that I had this entire, was that once you got the area from the Z-score chart, you would divide that by 2, because all of the areas in the Z-score chart are.
No, you're thinking backwards. So, if this was a two-tailed test, the p-value would be twice that. Yeah, so, yeah, I like the way you think about it, it's just backwards,
Or at
right?
least that's
So this one I didn't have to double because it's just a one-tailed test. If it was a two-tailed test, I would double the number that we get to be the p-value. That would make it fair to compare to alpha because that got put in the two tails. So what was alpha again? Is the p-value less than alpha? Yeah, that p-value, I kind of wrote it kind of evil, but the p-value is definitely, 0.0018 is less than 0.0050, right? So that means we can reject, but we already knew that, because 292 is way the hell up there. I already knew that we made it. So we can reject the null, we can support the
Is O always gonna be the null?
yes. Yeah. O is just my affectionate name for it. Its official name is the null hypothesis. And you actually read this symbol as H naught. Little zeros like a naught. Not like NOT, it's actually NAUGHT. Because English is weird like that. Okay, so how do I write my conclusion? What do I have to look at before I start to write my conclusion?
The claim.
The claim, good. So the very first thing I worry about is the claim, and the very last thing I worry about is the claim. Which one was the claim, HO or HA?
HO.
HO, the claim was HO. Therefore, I want to use this language, not this language. So did we succeed? Did we make it? Yeah, we made it in there. So we have found sufficient evidence to reject the claim that at most 55% of Chicago residents have an unfavorable view. Whoops. Oh, that's too many words. Unfavorable view of their local police. Okay. Pretend like that's what that says. I sort of had an episode there, an unfavorable view of this. So basically, if you want to put that into real English, we showed that the Chicago policeman's claim looks to be false. We found evidence that it's wrong, that actually more than 55% have an unfavorable view of their local police. Okay. Lock it. All right. Do you guys want to do 7 more problems or no more problems? I get the feeling you guys are feeling a bit depressed. I'm going to let you guys out. You should have everything you need to be able to do every section in chapter 9. So the last thing we need to do is section 10.2. So that's what we'll do next time. We'll do chapter 10. I can't off the top of my head remember when our next test is. So we'll kind of review that next time, see what's going to happen, see if we'll have one more quiz or not.